SwayamPrabha. Digital India. Educated India.
Hello, this is a continuation from the previous video where we were discussing about the temperature effects on the mechanical response of polymers. So, here is a quick recap from the previous video where we looked at how temperature affects the mechanical behavior and said that this ratio T by Tg determines how the particular polymer behaves. And we have seen at different polymer behaviors ranging from brittle, semi-ductile, ductile and elastomer behaviors. So, we were discussing about the different regimes an amorphous polymer shows, saying that it can at low temperatures it shows the glassy regime and then the transition regime, rubbery, viscous, and not for amorphous but for a crystalline polymers we see this decomposition at very high temperatures. So, previously we have only seen about the glassy region, but let us now look into the remaining 4 regimes. So, we will start with viscoelastic transition, it is also called as glass transition. So, let us say we start from a glassy state and then increase the temperature. What happens? As we increase the temperature, the secondary bonds melt or those bonds are broken because there is enough thermal energy to break those bonds. And then because of these breaking of the bonds, what happens is these polymer chains are now free to slip or slide against each other. Now, since these polymer chains are slipping or sliding against each other, that is when the modulus suddenly drops or the change in the modulus is very high. Now, we will do deep into why this modulus drops and why is this large. This can be explained using a concept called as reptation. So, in this figure we will try to visualize what reptation is, but let us first see what is its definition. So, we say that polymer chain is in a tube surrounded by molecules. So, this is the tube we are referring to and this is the molecular chain we are looking at. But what we say is we are discussing about this molecular chain which is embedded in a tube, but it is surrounded by molecules, which means there are several other polymer chains, maybe they are crossing against. So, these are all the polymer chains. So, we are talking about an amorphous polymer, that is why the structure or the packing is at random. But now let us focus on this blue polymer chain, and whenever we talk about this tube, it is a fictitious thing, which means there is no physical tube which we can find surrounding this polymer, but just for a thought experiment let us assume that there is a fictitious tube around this chain. So, now what I will say is what happens when we load this polymer. Okay. So, on loading these molecules slide in the tube. So, for example, let us say we are applying this load in this direction, in the vertical direction, a tension load. So, now if you focus on this particular chain, what will happen is this chain will slide in this tube independent of the surrounding molecules, it is just sliding in the tube. Because of this sliding we get an extra strain. This kind of behavior is what we are talking about reptation. We are not talking about changing in the shape of the polymer, we are only focusing on single chains and then saying that it will slide, it will retain the same shape. So, for example, this particular polymer chain, because it is sliding in the tube, it will not change the shape, but what is changing is it is sliding. So, the neighbors are slightly different. So, in summary, we are trying to say that this reptation is one mechanism by which the strain increases. As the strain increases, the modulus decreases. But this is not the only reason why the modulus decreases in this glass transition. The majority of this strain comes from when we go above the glass transition temperature, the free volume increases. What is free volume? This is the additional volume because of the jiggling of these carbon chains or the molecular chains. Now that we have this free volume, what happens? It allows the regions to slide. Now the molecular chains are free to move past each other, and this further decreases the modulus. So, the decrease in the modulus is a combination of this reptation as well as this the increased free volume. This is the reason why we see that there is a large decrease in the modulus in several orders or magnitudes. But now let us see, this is all when we load it. After we load it and leave it, what happens to the polymer? It goes back to the original position, and the reason why it goes back is because it has few non-sliding regions. So, again we are saying that this is not a homogeneous polymer, which means the density is not the same or the packing is not the same throughout. There are some regions where the sliding does not occur. So, since this sliding, let us say, does not occur at this point or this region, these corner regions, when we unload, these regions will help the polymer to bring it back to the original shape. So, what we are seeing in this glass transition is there are two things which help to achieve these large strains or the large decrease in the modulus. These are this reptation mechanism and the increase in the free volume, which leads to movement of these chains, and that explains the large changes in the modulus. But now let us see what happens if we further increase the temperature beyond this viscoelastic transition region. That is when we see a rubbery behavior. What is a rubbery behavior? Where we have a large stretch or the large deformation, and the stresses are more or less the same, or we have a plateau in the modulus versus temperature plot. But this rubbery behavior depends on the average degree of polymerization. Previously we have seen what is degree of polymerization. It gives a idea about how long these molecular chains are. So, if this value is less than 1000, it is hard to see the rubbery behavior, because then the molecular chains are too short. These are not too long, like in the other case when we are talking about more than 10,000, that is when we see the rubbery state. When the molecular chains are small, it is very difficult to entangle each other. So, that is what we will discuss next, saying that this rubbery behavior is mostly because of these entanglements. What are entanglements? Which we already discussed a few videos back. We said these are the knots between chains. Because these chains can take very random shapes because of their length and flexibility, they can also form knots, which means they can interlock with each other by forming these knots, which we call as entanglements. So, this is an representation of entanglements. Okay. But what happens at these entanglements? They give shape to the polymers, which means once you load, these entanglements will help bring the polymer back to the original shape. But let us look closely what happens during loading and unloading. During loading, the segments between them straight, which means let us say these are two different entanglements. Between these two entanglements, when we are loading, the polymer chains stretch or align in the direction of loading. But once we release the load, because these entanglements cannot be loosened, they bring these polymer chains back. So, these intermediate chains between the two entanglements, they wriggle and return back to the original or the equilibrium state. Okay, now let us see, it is not like every time we have these entanglements, it all depends on the polymer structure. So, when we look at amorphous polymers, amorphous meaning that there are no crosslinks, so which means it has only entanglements. So, it shows rubbery behavior only when there are entanglements, and as we have seen here, these entanglements happen when these polymer chains are long. Okay. But now, if we look at elastomers such as natural and synthetic rubber, they have both entanglements, So, they have both these entanglements and very few crosslinkers. So, the example is here. So, here I am showing you crosslinks. So, let us say if there are very few crosslinks like 1 in 100 or 1000, and then we also have these entanglements, both of them do the same purpose, which means after loading they bring the polymer back to the original position. That is why it brings the elasticity to these materials. Okay. So, now let us see what happens if we further increase the temperature beyond this rubbery behavior. That is when we get the viscous flow. So, this usually happens above 1.4 times the glass transition temperature. So, at that temperature what happens is, of course, beyond Tg the secondary bonds melt, but if the temperature is much beyond Tg, then there is enough energy in these chains that these entanglements slip. So, previously we said these are these knots which are locking these polymer chains, but now then since there is more energy, which means the chains are more agitated or wiggling. So, because of this they naturally come out of these entanglements. So, which means both the secondary bonds and the entanglements which are holding these chains together are broken. Once they are broken, now it behaves like a fluid or it shows a viscous flow. So, usually this is of advantage because most thermoplastics we blow mold them. So, blow molding is a manufacturing process to prepare hollow components such as the water bottles. Usually what they do is they heat the polymer to temperatures about 1.23 to 1.5 of the glass transition, because at that temperature we have seen the modulus is less and it is free to flow, which means the energy needed to blow, which means you need to have a air bubble which needs to be expanded, and this is you need to blow the air which is opposing this movement of the polymer. So, since the polymer is less stiff or the modulus is less, the energy required for this blow molding is less. That is the reason why these temperatures are chosen for this process. So, again what happens to network polymers like thermosets? They do not flow. The reason is because of the heavily crosslinks or the highly networked structure, there is no chance of breaking these bonds at these temperatures at least, and that is why we never see these viscous flow for, let us say, thermosets. But let us say if we are talking about thermosets and we keep heating or the temperatures are very high, then we see this decomposition. At very high temperatures there is enough thermal energy to break those covalent bonds. That is what we call it as depolymerization, because polymerization is bringing these monomers together. Depolymerization now means that we are breaking these polymer chains sometimes into smaller lengths or maybe even monomers. So, this is also called degradation of polymers. So, usually we avoid this decomposition, especially let us say we are using a particular polymer at high temperatures. We try to choose these temperatures such that these are slightly below these decomposition temperatures, because once decomposition happens the properties of the polymers degrade or the strength and stiffness of the polymers is very less, it cannot sustain any of these loads to continue with its operation. Okay. With this we complete the different stages or the different regimes of the polymer which a polymer can take depending on the temperature. So, this all can be summarized by something called as the modulus diagram, and here we will also look at how the cross linking, if we increase or decrease cross linking, how will it affect the modulus values. So, here is the modulus variation with normalized temperature. Here is this value of 1.0 or the glass transition temperature. Okay. So, here we are looking at what happens when cross-link density increases. So, let us look at the two extremes. The curve here is the for amorphous meaning there is no cross links at all. So, the only thing which is bonding these polymer chains are the secondary bonds. So, until now we have been seeing for an amorphous, until here we get the glassy region, and from here to here we have this glass transition or the viscoelastic transition. And slightly above this, slightly temperature slightly above, we get this rubbery behavior. And after that we have this viscous flow. But now in the other extreme, if you are talking about a very highly cross-linked polymer such as this, then we have this of course initially there is a glassy behavior, there will be a glass transition behavior, but the variations in the modulus will be very less. So, let us say somewhere here, and then there still is something called as a rubbery behavior, but if the temperatures are very high, this is when it decomposes. So, let us say this is the temperature beyond which the polymer decomposes. So, one example of looking at this cross linking is we can think about vulcanization. What is vulcanization? So, when we add sulfur to natural rubber, the strength or the stiffness of the rubber increases. This process of adding is called as vulcanization. So, during vulcanization, what is the sulfur doing? The sulfur is trying to create these cross links between these polymer chains. So, here we gradually see these are like few cross links, and moderate, and let us say these are high cross links. So, as we increase the cross links, what we are seeing is first molecular curves are pushed up. So, these modulus diagrams or these curves are going up. What does going up mean? They are becoming stiffer and stiffer. The reason is because more and more cross links means they are forming more crystalline forms, and we already know that crystals are much stiffer than amorphous because crystals are more densely packed and they have more of these covalent bonds. And we also see this, the amount of rubbery behavior also increases. So, which means if we want more and more rubbery behavior, what is rubbery behavior? Where it stretches for large strains and when unloaded it comes back to the original shape. So, if we add more concentrations of sulfur, that is when we can see more of this rubbery state. Okay. So, with this we conclude this video, and let us summarize by summarize the different regions we have been discussing till now. So, we started with glassy regime in the previous video, where we said that the chains are packed tightly. We observe secondary relaxation because of the loose sides, and once we know the fraction of covalent bonds, we should be able to estimate what is the modulus of the polymer. And with few examples, we have seen why fibers are very stiff and strong. Next is the glass transition, which we covered in today's video. It talks about as we increase the temperature beyond glass transition or about the glass transition, that is when we break the secondary bonds. And then there is a large decrease in the modulus, mostly because of reptation and increase in the free volume. And if the temperature is much beyond this, it is beyond the glass transition, that is when we get into the rubbery region, where the modulus decreases to about 3 megapascal, starting from 3 megapascal for glassy regimes. And whether we have a rubbery regime or not depends on the length of the polymer chains or the average degree of polymerization. And entanglements are the ones which help to get these rubbery behavior, in addition to few crosslinks depending on which polymers we are talking about. So, if the temperatures are further increased, that is when these entanglements also slip and we see this viscous regime. Decomposition is something we only see in crystalline polymers, where because of high temperature and thermal energy we are now breaking the covalent bonds, and this leads to depolymerization, or we also call it as degradation of polymers, because the properties of the polymers are now decreasing, the modulus decreases and even the strength decreases significantly. So, with this we have summarized what are the temperature effects on the polymers. In the coming video we will see about how time affects the behavior of the polymers. Thank you, see you again.